Welcome to a class about two subjects very close to my heart, and I hope to yours, mathematics and music. I'm a professor of mathematics at the St. Mary's College of Maryland. That's Maryland's public honors college. And I've been there for more than a decade, but I've been playing violin for 3 decades in orchestras, quartets, and various groups. Now, the opening music that I was playing was Bach's Prelude from Partita No. 3. We're going to have music throughout this course illustrating mathematics. But first, I want to tell you a little bit about how mathematics and music are connected for me. When I interviewed for the position at St. Mary's College, Richard Stark interviewed me. He's a short Austrian gentleman. And the first thing he said to me, he said, "I see you play the violin." He's very proud of his accent. And playing the violin is at the end of my resume with all the extra things. The next question he asked was, "Can you play the Bach chaconne?" If you don't know about the Bach chaconne, Bach wrote 6 partitas and sonatas for solo violin with nobody else on stage. And the chaconne is sort of seen as the pinnacle of all of this. It's 15 minutes of incredibly challenging music. It was actually once described by Brahms in the following way. On one stave, for a small instrument, the man writes a whole world of the deepest thoughts and most powerful feelings. So that was the piece that Richard was referring to when he asked me about the Bach chaconne. Now, this was an interview, and I didn't want to admit that I couldn't play it, so I said I could play other unaccompanied Bach, and then I did admit that I could not play the chaconne, to which Richard responded, "Well, you cannot have the job." Apparently, nobody with a PhD in mathematics that year could play the chaconne, and they gave me the job at St. Mary's College. The point here is that math and music are intimately connected for me, and I hope by the end of this course they will be for you too, no matter if you're coming more from the math side, or from the music side, or like myself, from both. Every course of mine at St. Mary's is structured around a single central question, and this course is no different. The central question for us is the following: how can mathematics help us understand the musical experience? And when I say musical experience, I mean the entire musical experience, from the single vibrating string or a vibrating tube of air, like a violin or a flute, putting those notes together to get a scale or a chord, and putting multiple instruments together to get some complex Bach piece, a sonata, a partita, to finally how music is delivered to us digitally in this day and age, on a CD or downloaded as an MP3. Now, the philosophy of this course is maybe a little different from the math you had in school. In school, mathematics and other topics tend to be taught in isolation. Mathematics and music might seem to be very separate, and they certainly were in school for me. Our philosophy is different. It's to show the connections between these two beautiful subjects. When we see mathematics, we're going to illustrate the math with musical examples, played on my violin or with other recordings. When we hear music, we're going to explain the underlying mathematics to help you understand the music better. Throughout this, we're going to draw on many different connections from different disciplines. We're going to talk about different areas of mathematics. We're going to talk a lot today about physics. We're going to talk about music history in general. We'll talk a little bit about music theory, and we'll in fact talk a little bit about art. If some of these are unfamiliar, that's okay. The key here is the connections among these things. So where should we start? Let's start where we usually start, with an A. Here's an A on a violin. That's called a 440A, and we're going to talk about what that means in a bit. Now, instruments look different, but they all have something in common. When an instrument plays, something is vibrating, causing a wave of pressure changes that travel through the air and finally get to your ear. The mathematicians have studied vibrating objects extensively, and their work helps us understand the sounds produced by all of the instruments in the orchestra, and eventually that'll help us understand music. So when we hear something vibrating, what are we actually hearing? When we play a 440A, and here it is again, we might ask what frequencies are produced. Well, we call it 440 Hertz, and that's after the 19th century German physicist Heinrich Hertz. The higher the frequency, the more times the waves are vibrating per second. And in particular, for a 440 Hertz, the waves are coming 440 times per second. Now, you might think that what's happening is the string is just sort of going up and down 440 times per second. Surprisingly, it's a much more complicated motion than that, and there are a lot of implications to that. With help from Gordy in the audio booth, I'm going to play an A, and we're going to see the spectrum We're going to talk a little bit more about the spectrum later. Now what you're going to see is that we have peaks, and the peaks come at different frequencies and they have different heights. So here again is an A. And what the spectrum is showing you is that the string vibrates at many different frequencies all at the same time. Let's look at the frequencies that are produced when you hear a particular note. If we were to play a note at 100 hertz, so something vibrating back and forth 100 times per second, the frequencies when we looked at the spectrum would be at the following numbers. They would be at 100, 200, 300, 400, 500, 600, on and on up. The higher the frequency, the higher the pitch. Now pitch is what musicians talk about to talk about the lowness or highness of a note. And these higher frequencies are higher in pitch. They're more in the soprano range and less down in the bass range. The lowest frequency produced in the case of this example, the 100 hertz, that's typically called the fundamental. And when we say a 440A, 440 hertz is the lowest frequency produced. If instead of looking at frequency, we would want to look at wavelength, we could do that as well. And when we talk about wavelength, you should think actually of ocean waves. When we talk about wavelength, we're measuring from the peak of one through the trough to the peak of another, a full cycle of that. You could also measure from the trough back to another trough, or from some midpoint back to the midpoint. You have to take a full cycle into consideration when you talk about the wavelength. Now sound are actually pressure waves, so nothing's going up and down. It's the pressure that's coming. Parts of the air are compacted and parts of the air are rarefied. A 100 hertz note has a wavelength of about 3.4 meters. And if we measure the wavelength of the overtones instead of the frequency, we see that those are things like 3.4 meters for the fundamental, and then 1.7 meters, and then 1.13 meters, and then 85 centimeters. And if we take that largest one, 3.4, as our measuring stick, we see those are in a ratio of 1, 1/2, 1/3, 1/4, 1/5, 1/6, on and on and on. The frequencies and wavelengths satisfy a key equation that the frequency times the wavelength is going to be constant. And in fact, the constant it's equal to is the speed of sound. Now, of course, the speed of sound isn't exactly constant. It changes depending on the pressure, for instance. If you go up to altitude, the speed of sound will be slightly different. But in any one place, the speed of sound is roughly constant. So if we play a 440A, what frequencies are produced? Well, we now know that, and we can see that in the spectrum. It's 440 hertz, and then 880 hertz, 1320. These are all the multiples of 440. The fundamental frequency is 440, and then we just add that again and again. Mathematically, we talk about this as an arithmetic sequence, and the important thing for us is that it's additive. To get from one to the next, we're just adding the fundamental frequency each time. How is it that a string vibrates in so many ways at the same time? Well, we actually have a demonstration to show you that. So imagine this vibrating string blown up to the size of this jump rope. And when we vibrate this string, the mathematics is telling us that it vibrates at many different frequencies. And we can see that on this string. Now musically, this is called the fundamental. And what you want to notice is that there's a flat place in the middle. There's a place where the string is exactly horizontal. We can actually get the string to vibrate in a different mode, and that looks like this. Mathematically, we're talking about the second harmonic. Musically, we're talking about the first overtone. They're always off by one when you describe that. And you'll notice that it has one node in the middle. There's a place where the string isn't moving at all. It also has two flat places. These are places where the string is exactly horizontal. We can get a third mode vibrating here. Here's the third mode. Now there are two places where the string isn't moving. Those are the two nodes, and there are three places where the string is horizontal. This is called the third harmonic, or it's called the second overtone if you're talking to musicians. I think it's quite surprising that our violin string is doing all of these simultaneously. Listening to a single string vibrating is like sitting in front of an orchestra of jump ropes. Each one is vibrating in one of these particular modes. That's why we talk about it as a symphony in a single note. A single vibrating string is actually many, many different frequencies. So let's actually hear what these sound like. Remember, what the mathematics is telling us is we're getting different frequencies all vibrating at the same time. And those are giving us different pitches, how high and low these different overtones are. Now you have to be careful when you talk about pitch and frequency. Pitch is actually the perceived highness or lowness of the note. whereas frequency is the physical thing. And we'll see in lecture 3 when we talk about auditory illusions that pitch and frequency are actually different. In this case, the overtones vibrate at different frequencies. We hear a single pitch. And the spectrum shows us all of the different frequencies that are vibrating. So I want to play for you all of the frequencies that you're hearing, or at least the first 8 or 9. Here's the fundamental. And here's the first overtone, also called the second harmonic. Here's the next one. After that. I want you to note that all of those notes are on the notes that you can find on a piano except the 7th harmonic. And that's an interesting fact that we're going to come back to a little bit later. We can look at the frequencies and the wavelengths of these. And if you look at the wavelengths, what you see is exactly what we saw on the jump rope. We see that the fundamental has a wavelength of the full string. In fact, it's double that. But we're going to talk about sort of one loop of that. One loop of that is the full string. And then the next mode, the next harmonic, vibrates so that the loop is just half the string. And the next one is just a third of the string, and then a fourth of the string, a fifth, a sixth. Mathematicians have a name for this. If you've had calculus, you would have heard this. It's called the harmonic sequence. It's sort of ironic. Mathematicians teach this all the time, and many times without noticing that that's where the name comes from. It comes from the harmonics that you can play on a string. The relative frequency of each overtone is now in a ratio of the following. It's in a ratio of 1 to 2 to 3 to 4 to 5. And if you remember back, the key equation here was that the frequency times the wavelength gives you the speed of sound. Mathematicians write this F times lambda, the Greek letter lambda, is equal to V. And V stays constant in any one place. And so if you look at the relative wavelengths versus the relative frequencies, you can see this equation in working. If you multiply the frequency by 3, you have to divide the wavelength by 3 in order for them to multiply and get the same velocity, the same constant, the speed of sound. What mathematics do we need in order to understand this? Well, first we need calculus. Calculus is the study of change. But we also need something called differential equations, which uses calculus actually to predict the future. That's sort of the point of differential equations, to be able to predict what's going to happen in the future. And we need a subfield of differential equations called partial differential equations. Partial differential equations is when you have more than one variable going on. Now, we're not going to go in depth with this mathematics. I just want to give you an idea of what's going on when we look at this mathematics and what the results of this mathematics tell us. There are 3 steps to understanding and using any mathematical model in order to predict the future. The first step is always to create a model, to use variables, to talk about your assumptions, to figure out what's going on, and to mathematize the situation. The second step then is to connect the variables. We have to figure out how these variables are related, and we use equations, and sometimes we'll use physics and things like that in order to connect the variables. And finally, the third thing that we have to do is we have to solve the system. We have to use these equations to predict what's going to happen in the future, to get a function which represents what will happen for all time after that. Now, if we do this well, then the result predicts, it actually closely models what happens when we see it in reality. If we don't do it well, then our prediction doesn't closely match reality, and then we have to go back. We have to go back to step 1, change our variables, change our assumptions, tweak the model a little bit, and go through the whole process again. So what does this look like for a vibrating string if we do this process of mathematical modeling? In our case, x is going to represent the distance along the string, where x equals 0 right here at the bridge, and x equals, well, let's just call it L here at what's called the nut of the violin. Let's just assume that's 1 for now to make our calculations easier. Now we're also going to have other variables in here. Small t we're going to use for time, and capital T we're going to use for the tension on the string, because these pegs are holding this string in with a particular tension. We also have to talk about the weight of the string, and we usually use rho for that, another Greek letter, and that stands for the mass per unit length. We're going to just call it weight. Now, if we want to talk about this moving, we need to give that a variable, and we talk about u of x and t being the height of the string at position x and time t. And so u of x would be some number that tells us how high the string is. One of the assumptions that we make is that we're going to at least initially assume that our string just vibrates up and down. That's, of course, not what it really does. It sort of moves in a circle like this, but that will actually be close enough for our purposes. The next step is to connect the variables. And if we want to connect the variables, we need some equations to do that. And in this case, we're going to use Newton's laws. One of Newton's laws is that force equals mass times acceleration. And when we translate that into this particular situation, we get that the tension times the second partial of u with respect to x is equal to the weight times the second partial with respect to t. Mathematicians give this equation a name. It comes up so frequently. We call this a wave equation. We actually need a little bit more information. We need boundary conditions. And the boundary conditions for this particular problem are fairly simple. We know that the string is never going to move here. This is the position x. And so u of 0 and t is equal to u of 1 and t is always equal to 0 for all time t. We also need another thing called initial conditions, and that's the following. If we were to deform this string into some shape, some function f, and then let go, we could use this model to predict what's going to happen. And so again, the initial conditions are to deform the string and then to just let go. The next step in our process is to solve the partial differential equation. Now, we're not going to go into the details of solving a partial differential equation. If you're interested, the reading list suggests several readings that would do exactly that. A partial differential equations course in an undergraduate mathematics program would do this as well. The point here is that when we solve these partial differential equations, we predict the future. Given any initial condition f that I deform my string into, the mathematics tells us what's going to happen for t bigger than 0, for all time in the future. The power of differential equations is exactly this. If you can model the forces that act on a system, the mathematics predicts what will happen in the future. And that's an amazing thing that mathematics does. So let's look at the solution that we get when we solve this particular PDE. We get u of x and t is equal to the sum. The capital letter sigma stands for sum. And what we get is that it's a sum of sines and cosines. One of the assumptions we've made before we solve this is that the tension, the length, and the weight are all equal to 1 for now. We'll come back later and revisit this model in the case that they're not 1. This mathematics is telling us that the string is vibrating in a series of modes. Mathematically, what we're getting is the sum of sine waves. Musically, what we're getting is a series of overtones. Now, these numbers ak that you see out in front of these, mathematically, these are the Fourier series coefficients. These are just numbers. Each ak is a single number. Musically, that's telling us how much of each overtone is produced. When I take my violin and I pluck a single string, just like this mathematics is telling us what we already saw in the spectrum, that we hear a symphony of different frequencies when I just pluck this single string. So what about other instruments? The beauty of mathematics, one of the wonderful things about mathematics is that it's universal. You know, once we've developed addition so that we can add 2 apples to 3 apples and get 5 apples, we can do that same addition with bananas or any other fruit. And once we have algebra that models a biological situation, that same algebra can be used in economics. It can be used in lots of different fields. It models the same thing. The algebra stays the same. Interestingly, wind and brass instruments involve vibrating air columns, but the mathematics of the situation is almost identical. Like a string, a tube of air resonates in particular ways, modes, much like the jump rope that we had up here earlier. What you hear is a combination of those modes, literally a sum of all of those different modes. We can hear this in an interesting example of just a single swinging tube. So I want you to think about this swinging tube as modeling a wind or a brass instrument. So here's my tube. I actually bought it at the local pool store. It's just a plastic corrugated tube. It has these bumps in it. And when we swing it at different speeds, we find the resonant frequencies, and you can hear it. First, I'll play a few of these notes. And again, you get a particular sequence of vibrating modes, just like we heard on the violin. And again, they're additive. What we're hearing are maybe 400 hertz, 600 hertz, 800 hertz, 1,000 hertz. What we see is that they're additive. They're differing by the same amount every time. It's another arithmetic sequence. Now, it turns out that we're missing the 200 hertz, and that has to do with technical physics reasons with corrugated tubes. But like strings, brass instruments and wind instruments produce a symphony of different sounds in a single note, a symphony of different frequencies, and those are the vibrational modes. Now, one of the things that you can do on a corrugated tube like this is you can play simple songs. In fact, you can play taps. It's actually not surprising that you can play a song like taps. You see, taps is traditionally played not on a trumpet, but on a bugle. A bugle has no valves. You can't change the length of pipe that's on a bugle. So it's just a single vibrating tube. And the mathematics of that is very similar, and you get exactly these overtones. Those are exactly the things you can play on a bugle, and those are exactly the notes that we can get on this particular vibrating tube. So let's look at the spectra of other instruments. We're going to listen to a couple of different instruments and see them played. Each instrument is going to play an A, and the spectrum is going to show us that we hear a sequence of different frequencies, the overtones. I want you to notice a couple of things about this. All of these produce more than just one frequency. There's a fundamental, and then there's many other peaks in the spectrum. And each instrument has essentially the same patterns of frequencies. Again, it's additive. It's just multiples of the fundamental. How much of each overtone? That we're going to talk about in lecture 2. So let's listen to a couple of A's from different instruments. Here's an A on a clarinet. Here's an A on a flute. Here's another. Here's a bass guitar. Here's an A on a trumpet. Here's an A on a piano. So I hope what you saw in those is that any instrument is going to produce a sequence of overtones, and there's a pattern to those frequencies, and for most instruments that's called the harmonic sequence. When we're looking at frequencies, those are just multiples of the fundamental. The ratios are 1 to 2 to 3 to 4 to 5 to 6 to 7, just the natural numbers. If we're looking at wavelengths, we get the reciprocals over those, fractions flipped over. We get a ratios of 1, 1/2, 1/3, 1/4, 1/5, 1/6. The mathematics that we use, differential equations, correctly predicts what's going to happen, correctly predicts that we get these particular sequences of numbers. Now I want to show you an instrument with a different set of overtones, and we have one here. This is a timpani. We have to move, to get a set of different overtones, we have to move from one-dimensional objects, strings, vibrating columns of air, these are all one-dimensional, to something that's two-dimensional. And so we're essentially moving from the strings, brass, and winds in an orchestra over to the percussion. This drum head here is two-dimensional, it's flat. And when you play the drum head, you get different vibrating modes, just like we do on a string. Now, I can play this here, and I'll play it for you here. And we can look at the spectrum and see exactly what it looks like. And when you look at the spectrum of a timpani, when you look at that spectrum, you see that it doesn't have the same structure of the other instruments we've had. There isn't one nice peak, nice fundamental, and then overtones above that. It still has some structure, but the peaks are not nearly as clear. They're much more chaotic. You simply don't have this nice 1, 2, 3, 4, 5, 6 pattern. The timpani still has different modes that it can vibrate in, and we can actually use this setup to see them. Now, one of the things I want you to note, and we're going to explain this in a minute, is that when you play a timpani, you hit it out here, somewhat close to the rim. You don't put it in the center, and you can actually hear the difference. Here's when you play out here. And if I were to hit the timpani in the center, it sounds much more dead. You don't get that nice reverberation. So let's look at what the modes on a timpani look like. What I have set up here is I have the timpani, and then it's connected to this, this vibration mechanism, which vibrates this piston up and down in a particular way. What this is connected to is it's connected to a frequency generator. And when I turn this on, this frequency generator is going to vibrate this at exactly particular frequencies. And I'm allowed to change the frequencies on this setup. And so I can change the frequencies. And one of the things that's interesting about this is I'm not changing the amplitude at all. When we turn this on, you're going to hear that the volume that you hear changes dramatically. And that's not because this is vibrating at greater and greater amounts. Instead, that's simply because this particular drum has particular resonances. So that's the setup we have going here. So let me turn it on for you. Now this drum head already has a line drawn on it on the top, but so to allow us to see these modes, I'm going to sprinkle poppy seeds on the top. And what's going to happen is when the drum head vibrates in a particular mode, say if the drum head is vibrating like this, then each half of it is going to go up and down, but there's going to be a line in the middle where the drum head isn't moving at all. And we can actually see that because these poppy seeds will accumulate in the places where the drum head isn't moving. So let's see if we can see that. The first mode we're going to see is this half and half. So half the drum head is moving up, the other down, and there's a line through the middle where it's not moving. The next one is quarters. So a quarter of the drum head is moving up, a quarter down. You can see there are two lines, a big plus sign where the drum head is not moving. We need to add a few more poppy seeds to see these. And as we go to higher and higher frequencies, you can see that the lines become more complicated. Here's a particularly complicated one that looks like almost a sine curve coming through the middle and two parabolas on each side. And sometimes they're really sharp. You can see how quickly the poppy seeds move into position along the nodal lines where the drum head isn't moving. Now, one of the things you'll notice about this is that most of these patterns actually go through the center. What that's telling you is that the center of this drum contains most of the nodal lines. Now, when you hit a timpani, when you play away from that point. You see, if you play at a nodal line, that's where the drum head is not going to move at all. And what you want to do is you actually want to hit in a place where the drum head is moving a lot. So you don't hit at the center where all the nodal lines are. You hit here near the side where it's in the middle of these notes. And that causes the drum to vibrate in exactly those modes. Once we understand the overtone sequence of an instrument, we can then start playing an instrument. And we can vary the frequency of the fundamental. If we couldn't do that, music would be very uninteresting. We would have only a single note. That's not very interesting music. So how do we change the pitch of a single note? That question, it turns out, is highly mathematical. How does the frequency of the fundamental depend on things like, in the case of a violin, the weight of the string, the tension, and the length? Let's look at some qualitative answers first. If the weight of the string increases, the vibrations are going to slow down. That makes sense. If you make something heavier, it goes slower. But you can also see that my G string here is a much thicker string than my E string over here. And the G string is a much lower note. Here's the G. And here's the E. We also know that if the tension increases, the speed of the vibrations has to speed up. We can do that. We can tune something. Here's my D string. And if I tune it up, if I increase the tension, you hear the frequency going up. We also know that if the length increases, the vibrations are going to slow down. The frequency will go down. Think about cellos and basses. Those have long strings. Those produce low frequencies. Differential equations gives us a more quantitative answer. The question again is, how does the frequency of the fundamental depend on the string weight, the tension, and the length? And here we actually have a formula. The mathematics gives us this formula. The frequency is equal to 1 over 2L times the square root of T over rho. Again, L is the length of the string, T is the tension, and rho is the weight. We can see this formula at work. Again, if I increase the tension, the pitch goes up. And that's because the tension, the t here, is in the numerator of that fraction. When t rises, the square root also rises, and so the frequency goes up. If we increase the weight, the pitch goes down. And we can see that going from my E string here, which is the lightest string, to my G string, the heaviest one. And when we increase the weight, rho, appears in the denominator. So when the denominator gets bigger, that fraction gets smaller, and the frequency is going to go down. Now, you might ask about the tension. We actually have roughly the same tension on my G string and my E string. If we didn't have the same tension, then over time, my violin would be pulled to one side or the other. And we know that instruments, especially Italian instruments, have lasted hundreds of years. So that tells us that the tension has to be about the same. If you do the math, it turns out that the G string is about 10 times the weight of the E string. We can also look at length. When you increase the length, L is going up and L is in the denominator, and that tells us that the frequency goes down. The pitch is going down. Now you can think about that in terms of larger instruments, violas, cellos, or basses. You can also look at the strings of a harp. If you look carefully at the strings of the harp, the lower ones are long, and up higher, the higher ones are much shorter. You can see this inside of a piano as well. Where does this formula come from? It comes from differential equations. Remember, before we assumed that the tension, the rho, and the length were all equal to 1. And when we looked at that equation and we took k equals to 1, we got the fundamental. The fundamental frequency, how does that depend on t, rho, and L? Well, we could go back and run these calculations again and do exactly what we did before, the 3 steps going through and making a mathematical model and then solving that. And if we do that, here's the more complicated equation we get that involves now t, rho, and L. What does this equation mean? Well, this equation is saying that, again, it vibrates in many different modes. That's the summation. We have different overtones. K equals 1 is going to give our fundamental. And when we look just at the k equals 1 part, we get the sine of pi x over L times the cosine of this complicated expression. But you can see that that complicated expression looks a little bit familiar. That complicated expression is exactly giving us the fundamental frequency of our vibration. It's giving us that the frequency is equal to 1 over 2L times the square root of t over rho. That's coming from the cosine term. And if you're wondering about the 2 and the pi that aren't there, that has to do with the fact that the natural wavelength of a cosine is 2 pi. So now that we've solved these, mathematically we can create melodies in predictable ways. And so I wanted to show you how we do that on the violin with a piece. The first piece I ever learned, I was 4 when I started playing the violin, and the first piece I ever learned was Twinkle, Twinkle, Little Star. I want you to think about how each note is made of many different frequencies, the overtones, and how we're creating a melody by changing the frequency of the fundamental. And the way we're doing that on a violin is by changing the length. I'm going to put my fingers on the string, and that effectively shortens the string and makes a shorter string vibrate. And we're also changing the weight. And I'm doing that by switching from my E string to my A string to heavier strings. So here's Twinkle, Twinkle, Little Star. Now that was very simple. Let's think about a more complicated piece. Let's go back to the Bach prelude that we opened this talk with. Think about how quickly I'm changing the length and the weight of the strings that are vibrating. I'm creating music. Now I want you to know that if we had a professional violinist here, they would be even more accurate in changing the length. They would be even more accurate within fractions of a millimeter as to where they're putting their fingers on the string. Now, I haven't played as professionally for as long as a professional violinist would have, so I'm going to be a little bit less accurate. I also want you to notice that I'm using what's called vibrato. When my finger does one of these, motions like this, mathematically what's going on is that we're slightly changing the length of the string. What that's doing is giving us this sort of wavering sound to the pitch. Ah. That vibrato sort of takes the edge off of a note, and it gives a sort of a slightly sweeter sound to it. So here again is the Bach prelude. Now I want to move from changing pitches on a string to changing pitches on a vibrating column of air. Before we dig into the mathematics of a vibrating column of air, I actually want to demonstrate one of the instruments that some of my students made. They had a name for this instrument. They actually called it the Wonder Pipe 4000, but it's a fairly simple instrument. It just involves a PVC pipe and a bucket of water. Now, on a violin, we were changing the length of the string, and that was changing the pitch. On the Wonder Pipe, what we're going to do is we're going to change the length of the column of air that's vibrating, and that's going to change the pitch. And what happens is, as we move this pipe lower and lower, the water level stays at the surface of the water, and so the column of air that's vibrating is shorter and shorter. They've put lines on here to indicate where you should play a scale. Now, an interesting thing happens with the Wonder Pipe 4000 when you take it out of the water. Here it is with just barely the end in the water. And if I lift it out of the water, you get a much higher frequency. Let's go back and forth. Here it is in the water and out of the water. This difference actually explains a key difference between flutes and clarinets, and we're going to talk about that in a minute. But mathematics predicts this strangeness, this difference between a pipe in water and a pipe out of water. Now, what I said before is true. The mathematics of a vibrating column of air, for instance a flute, is very similar to the mathematics of a vibrating string. When we were looking at a string, u of x and t represented the height of the string at position x and time t. When we're looking at a column of air, u of x and t is now going to represent the pressure, the difference from atmospheric pressure that's in this particular tube at position x and time t. When you put this into equations, what you get is another version of the wave equation. You get that c squared times the second partial of u with respect to x is equal to the second partial of u with respect to t. Here c is the speed of sound, and we're getting that from fluid dynamics. For a flute, which is open to the air at both ends, one end that's obvious. At the other end, you'll notice that a flautist is not covering the mouthpiece entirely. The mouthpiece is open to the air, and they're blowing across that. So for a flute, the column of air is open at both ends, and that tells us that the boundary conditions are 0 at both ends. U of 0 and t is equal to u of L and t is equal to 0 for all time t. Now there's a key difference between a violin and a flute, and that difference is that when a violin vibrates, there's this sort of middleman in this process. The string vibrates, and then that vibrates the air. In contrast, when you have a flute that's vibrating, there's no middleman. It's the air within the instrument, within the flute, that's doing the vibrating. The length of the instrument actually determines the wavelength of the sound. So let's look and predict what the wavelength of sound is going to be from a flute. The wavelength of sound here, if we have a flute which has length L, then we think about setting up a wave within that. We're going to set up exactly what we had with the jump rope. We're going to get something which is 0 on both ends. Those are the boundary conditions. And then if we want to know the wavelength, we actually have to extend that. That's just half of that. That's going up, and now we have to go back down to get an entire wavelength. And so if we have a length of tube here, think about a flute, we know that the lowest possible frequency, the lowest note that we're going to have is going to have wavelength which is about double the length of the flute. We can check this. The lowest note possible on a flute is about 0.7 meters long, and we know that the frequency times the wavelength is going to give us the speed of sound. Well, the speed of sound is roughly 340 meters per second, and so we can solve for the frequency. The frequency should be the velocity divided by the wavelength, and we should get 340 meters per second divided by 2 times the length, which is 1.4 meters. And when we do that, we see that the lowest frequency a flute should produce is about 240 hertz. If we check and try to play a note on a flute, the lowest note on a flute is a B below middle C. That's what musicians call it. And it's about 247 hertz. We're incredibly close. Now what about clarinets? Clarinets play much lower. You might remember from hearing an orchestra that a clarinet has a much lower range than a flute. If you think of like the quintessential clarinet solo, it might be the opening of Gershwin's Rhapsody in Blue, where the clarinet goes do 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 do. It's this beautiful glissando. Now that might be a little bit weird because a clarinet and a flute are about the same size. Why is it that a clarinet can produce sounds so much lower than a flute? The lowest note on a clarinet is something around 160 hertz. That's much lower than the 240 hertz that we had for a flute. To understand this difference, we have to understand the boundary conditions. That's the key. A flute, remember, was open to the air at both ends. We got atmospheric pressure at the end and at the mouthpiece. In contrast, a clarinet is open at the bottom, the bell end of the clarinet, but it's completely closed at the top end. The clarinet player puts the reed entirely in his or her mouth. Pressure can build up against the reed, and that changes the mathematics of the situation. Before, the boundary conditions were that you had 0 at both ends. And now when we take into account the fact that it's closed at one end, we get that it's 0 at the bell end. There is no pressure change at the bell end. But at the closed end, we get that there's actually maximum pressure change. We get that u sub x, the derivative in x of x and 0, is always equal to 0. That's telling us that we have no displacement. There's nowhere for the air to go. It can't vibrate anywhere because it's coming up against the edge of the reed. We can actually see this if we think back to the jump rope. The mathematics is telling us that one end of the clarinet is like one end of the jump rope. It's held fixed. The other end of the clarinet is different. The other end of the clarinet has a place where the jump rope has to be flat. It has to be horizontal. The mouthpiece is, in other words, it's located in the middle of the loop of rope when we think about this jump rope. And we can use that to figure out the lowest wavelength that a clarinet can produce. So what is that wavelength? Well, we can think about a clarinet here, and here this end will be the mouthpiece and this end would be the bell, and you can follow the rope. The rope has to be not moving here, but it has to have maximum motion here. It has to have a flat point here. And if we want to look at the wavelength, well, here's the length of the instrument. We would have to go up and back down here, and that's only half the wavelength. The wavelength has to go up and then down and then finally get to the end. It has to do a full cycle. And so the length of the clarinet was only 1/4 of that length. That tells us that lambda, the wavelength for a clarinet, has to be 4 times the length of the clarinet. And we can check this. A clarinet is about 0.6 meters long, and the frequency produced, the lowest frequency produced by the clarinet should be, according to this mathematical model, the velocity, 340 meters per second, divided by 4 times the length. The length was 0.6 meters, and that gives us 2.4 meters. When we do the calculation, we get that the lowest frequency a clarinet should be able to produce is about 140 hertz, and that's really not far off. Let's compare a clarinet and a flute for a second. So a flute and a clarinet, again, are about the same length, but a flute can produce only notes as low as 240 hertz or so. A clarinet can go much lower, 140 hertz. They're about the same size, but a clarinet plays much lower. If you want to think about how much lower, we're going to have to study things like intervals. And we can study those mathematically, and we're going to do those in later lectures. The scientists at the University of New South Wales have done some very cool work related to acoustics and vibrating tubes of air. And you can see what they've done on YouTube if you search for a flute-clarinet hybrid. What they've done is they've taken a clarinet mouthpiece and mounted it on a flute. If you take a clarinet mouthpiece and put it on a flute, you now have what looks mostly like a flute, except that it's now closed on one end because it's a clarinet mouthpiece. And it turns out that can play much lower notes. They've also taken a flute mouthpiece and put that on a clarinet. And what you get then is an instrument which looks mostly like a clarinet, except now it's open on both ends and it no longer plays low. So let's go back to our Wonder Pipe 4000 now that we understand the mathematics. And that explains why we can do this. And now when you see a flute play, you should realize that it's an open tube at both ends and it cannot play very low. And when you hear a clarinet play, you know that it's closed on one end. This end would represent, the end down here would represent the mouthpiece where it's closed, and we get a much lower sound. Out of the water, higher pitch. It's a flute. In the water, lower pitch. It's a clarinet. I want to talk about one of the assignments I give to students, which is to use mathematics to build instruments. They build really interesting instruments. One is the Wonderpipe 4000 that they had here. Some of them will build things like flutes. One student, Ben Love, built something much more complicated out of PVC pipe. And I think this is just a rubber glove that he found in the kitchen. And all of their instruments have to use mathematics to produce sound at different frequencies. So let's see what we've figured out today. What we figured out today is a note played on almost any instrument includes many different pitches, different frequencies, called overtones or harmonics. For most instruments, those overtones are related to a harmonic sequence. In terms of wavelengths, that's 1, 1/2, 1/3, 1/4. In terms of frequencies, those are 1, 2, 3, 4, 5, 6. We make different pitches by changing the vibrations in mathematically predictable ways. Now I want to leave you with an interesting question to ponder, and that's exactly this. The mathematics of differential equations explains some of the differences between these instruments. Among other things, a clarinet and an oboe the mathematics is not the same because they're both closed on one end, but the hole inside of an oboe is actually a cone. It's not a cylinder. Inside of a clarinet, it's a cylinder. So you get different mathematics. Now, what we said today is that flutes and violins have the same exact mathematics. Why don't flutes and violins sound exactly the same? The answer has to do with resonance and timbre. That's the color of the sound, and that's the subject of lecture 2. We're going to finish this lecture the way we'll finish many of the lectures, with a sort of coda. That's the end part of a musical piece. We're going to end here with a piece by Vittorio Monti. This is a piece called Chartis. It was inspired by the gypsies of Eastern Europe. And I want you to think about how I'm changing the attributes of a vibrating string to produce different pitches. And we're using that to produce music. So here's Chartis.